tags, and you get kind of specialized morphology for verbs, specialized morphology for nouns, which seems to make a lot of sense. And we haven't been able to run this yet on the full joint inference, but when we constructed it such that we had gold standard tags in the data, we got a nice boost. So we do think there's some mutual benefit that can be had if we manage to get them working together. We can also do things with the hyperparameters, not just the structure, but going in and encouraging the behavior of the inference process. So we found that with very small amounts of data, we were already outperforming Morfessor, which is kind of the state-of-the-art system right now for morphology. So for English, we were able to do a little bit better when we had very limited training data. But when we boosted these, when we just went in and boosted the hyperparameters on the suffix productions, just because English is much more productive in its suffixes and its prefixes, we were able to get a nice boost as well. So that's the sort of thing. That's the sort of thing when you have a interpretable model, you're able to do. You can go in and kind of selectively do things that make sense to you. And then there's a lot of information that could potentially be included. You know, go as far as to actually attach features to different morphs and things like that if we know more about the language. And this is all unexplored terrain right now that we're interested in.
So the metric there was just how well you did the segmentation?
Yeah, this was the Emma score from Morpho Challenge.
The what score?
Morpho Emma. I'm not sure what the acronym stands for, but
there's some gold standard segmentation.
So for English, Zulu, a handful of these languages we had some gold standards for, fortunately, but most of them we don't.
So you don't have results for actually morphologically complex language?
Zulu is very morphologically.
Where was the Zulu? Oh, down there. Okay.
Sorry, it's not centered. And I had some. There's I don't know why I must have forgotten to put this in here, but we have Turkish results that are also like that.
Okay.
I mean, that's also a little narrow because they're both included in it. But we have Tamil and.
Wait, can I see the Zulu again?
Oh, sure.
So was it? Oh, I see. Okay. All right.
Yeah.
Sorry.
Oh, no. Okay.
So one other question. So how much work was, like, from one view, you're back to like handcrafting grammars.
Hmm.
So like, how much work went into building the Zulu grammar that did a lot better?
Not much at all. I mean, that was just the one that had the. Let me see. Okay, this one was a little more work, and it's interesting because at some point you want to start writing programs that write these for you. You know, so this was something where you wanted to have a separate morphological model for each part of speech tag, and you had to kind of keep things coordinated in a little bit more complex way, and you certainly don't want to do that as a human. I'm interested in exploring how we can define some intermediate representations between kind of basic things like a Bayesian network or an adapter grammar that kind of constrain. Well, adapter grammars are actually an example of this. They constrain the space of possible models that you can define, but they make it very easy to experiment with that full range within there. And so I think I think adapter grammars are a big success story of that. And I think that I'm interested in finding maybe other kind of high reward formalisms that might kind of encourage experimentation with a particular subset of the model space. Okay. But yeah, this was a little tricky in this one. Okay, now I think I only have a few more minutes, so I'm just going to go through a little bit of how I designed and dealt with some technical problems with the graphical modeling toolkit that I used for my dissertation work. So we wanted to use C++ for the high performance. So we created class hierarchies that correspond to different elements of Bayesian networks. And in fact, we actually used a factor graph formalism because it's equivalent to Bayesian networks, but it makes a distinction between the data and the distribution aspects of a node. So it's a little cleaner in that respect. So this graphical modeling toolkit that I made has a class hierarchy for data types, the scalar vector matrix, all combinations of real and integers, and then a bunch of kind of language-specific objects for things like representing Connell-style parsing output and stuff like that. That made sampling a little bit easier. The factors that I defined are all related to discrete distributions, like so Dirichlet categorical, conjugacy, beta and Bernoulli, and then a number of combinations and permutations of that, like hierarchical Dirichlet's. And there's a class for optimizers, which includes, so basically those are designed to operate on non-stochastic hyperparameters that we might want to optimize. So that included implementations for Minkin's fixed point iteration for Dirichlet beta priors. There's statistics objects that were for tracking the sufficient statistics for sampling. And then I think probably most interestingly, I wrote 3 different samplers. So these are basically 2 different strategies in terms of how they sample the nodes. So there was the basic serial Gibbs sampler that just ran through nodes in sequence, but then there was an OpenMP enabled and an MPI enabled sampler, which was we're able to take advantage of multiple cores and HPC systems respectively. And they would basically split up the node space, copy the statistics, and send it to different processors or machines, let them do the sampling for their subset, collect all of the results, and then reconcile the counts. And I think this is interesting because this violates some of the basic idea behind Gibbs sampling, which is that it has to be serial. And when you define Gibbs sampling, that's how it is. You have to update your statistics before you go on to the next node. You can't let them get out of whack. But it turns out that this works really well for at least these simple models. I know that some people have also done this for LDA. And so I'm curious about how far that can be pushed. I'm wondering how much parallelism we can add before we start to have convergence problems. And also what kind of models will cause more convergence problems. So if the nodes are more connected, is it going to cause more problems? And once we find that point where it starts to break down, I think it would be very interesting to start looking at kind of online ways of optimizing how we split up the node space and how we sample things in parallel. So maybe by some kind of runtime statistics about how the nodes are affecting one another, et cetera. So I think that's a cool area to look at that could kind of help pretty much everybody who uses Gibbs sampling. And I wanted to, I'm sorry.
I'm curious about why you decided to build your own toolkit as opposed to using things like Infernet, or was it not flexible enough for you?
Well, yeah, so there were some performance problems with some of the toolkits. So the toolkit that I was most interested in possibly using, I'm not sure if maybe I missed some when I was exploring the space, but at the time, JAGS was the one that I was looking at, and it was not performing well, and maybe even more importantly, it didn't have non-parametrics, and so one of the things that we played with was putting Dirichlet process priors on the syntactic frame so it could grow with the data. In JAGS and the Bugs family of modeling tools, you had to kind of code that in the modeling language, and it has terrible performance. So at least at the time, I mean, it's possible that some of that space has changed.
Jinka has Infernet, Microsoft there in Cambridge.
I'm not sure. I mean, I did look at something from Microsoft. I'm not sure. I don't remember exactly the motivation behind.
No, but it's just curious. I mean,
Yeah.
it's good.
Yeah. I mean, I enjoyed it. I enjoyed doing it. It was a fun programming exercise, which is why I'm talking about it in a research presentation. So I also the transformers. This didn't make it in, but I wanted to write something that would kind of do a pattern match on tree structure, and with the possibility of kind of replacing or transforming that tree structure into something else. So the classic case is collapse Gibbs sampling, where I would kind of match the conjugacy relationship and automatically collapse it into something that's easier to sample. But I thought that might be a cool feature to have in there, but I didn't quite get it all coded in time. And then we wanted to have a scripting language for data wrangling and flexibility. And for that purpose, we were using the Swig tool, which takes C++ headers and generates a comprehensive API and code for a dynamic library, your scripting language of choice. It's amazing how well it works, but it works even better when you write your code from the ground up with it in mind. So by making it part of the build system, kind of always had this really nice Python interface to the high performance code ready to go. And so I think that was very useful. It actually turns out that's how they built Attila as well. I was happy to see. So one of the particular problems that we dealt with was runtime polymorphism, which is a slight performance hit that you get when you are calling a virtual method on a base class, and it has to go through the effort of looking up the virtual table of functions and possibly following multiple links to find the appropriate function to call. So there's a small cost associated with that can add up if you have a function that's called very often, like say the sample function on a node. And also the compiler often has trouble optimizing around these boundaries, so it can't inline functions, for example, if it doesn't know what's going to be happening at runtime. And the ugly way to get around that is sometimes you just do a static cast, which relies on the programmer knowing for sure that the pointer that they're casting is, in fact, this derived type. Otherwise, you're going to throw in a runtime error, and that's bad. So the way around this was to use something called the curiously recurring template pattern, which is it's kind of code golf, but I like this idea. I kind of like how they figured this out. And the idea is that we're basically going to use the C++ template language to define a base class that takes as a type parameter its eventual instantiation. And so it can check that eventual instantiation at compile time to make sure it has the method that it's going to be invoked on it. So you basically eradicate the runtime polymorphism aspect, but you still get the type checking of the C++ language, which is nice. So I think that's sped things up maybe 50%, I want to say, having this instead of just having straightforward class hierarchies. And some impressions that I got from this coding was that I like how the C++ standard emphasizes functional programming, so there are a lot of higher order functions, lambda syntax, and immutable variables, which help reason about program semantics and guarantee correctness. And it can also remove some of the burdens associated with parallel computing. So my new favorite language is Haskell, which is kind of a supercharged version of all of those advantages. And there's a lot of focus currently on automatic parallelization, which is also something that I'm interested in. And writing domain-specific languages, which gets back to that designing intermediary formalisms idea. And I think performance is becoming more and more important to them as time goes on. So now just some broad research priorities and how I think they're linked to the center here. I'd like to continue to focus on domains and languages with high importance to resource ratios, so like the underrepresented languages in the Babel project, the unusual registers, genres, and topics, like these unusual subdomains of biomedicine. And I also enjoy this collaboration that this engenders with other fields and domain experts. But at the same time, I would also like to continue modeling some fundamental linguistic phenomena. So both of the projects that I mentioned today are kind of like that they're phenomena that are used in downstream tasks. I like this because they can provide that benefit potentially for a lot of different people. And I also like how they can be tied together to do joint inference, like I did with syntax and semantics. And I think an area that I would like to get some more experience in and spend some more time with, that fits in really well here at the center, is applications that model latent user, author, and speaker properties. So that's something that I haven't done much work with lately, but I've always had a long-standing interest in things like object identification and plagiarism detection, things that are getting at kind of idiolect type stuff as opposed to the kind of broader language properties that I'm also have been working on in the past. So thank you very much, and I'd be happy to answer any questions.